So good morning. Welcome to the day 3 of your calculus course here. We're going to finish vectors in space, and then we're going to begin the dot product. Woohoo! Good stuff. Okay, so some forms and facts for vectors in space. In the world of 3D, which is vectors in space, you also have two forms for denoting a vector, component form and the linear combination of standard unit vectors. But the component form for a vector in 3D, you're going to need three scalar components, the x, the y, and the z. And you still are going to have these angular brackets, and that's how you'll roll. Now, the other format, linear combination of the standard unit vectors, you're now going to have three standard unit vectors. The I, J, and K. Those are all unit vectors that point in the positive x, y, and z axes respectively. And so you can write a vector as a linear combination of those three standard unit vectors. Be able to do either one of those forms when you're typing in answers in my math lab, as well as writing handwritten work. Okay, so let's say you're given 2 points, and remember points use parentheses. That's how we know the difference between a point and a vector. Let's say you have point P and point Q, and they give you coordinates for both. And so you're out here in 3D. Here's point P, boom, there's point Q. Form the vector PQ. No problem. Just like in 2D, we learned how to do this. Terminal minus initial, terminal minus initial, terminal minus initial. You take the difference of the x, y, and z coordinates to get your x, y, and z components. And order matters, terminal minus initial. Otherwise, you'll get the vector QP instead of the vector PQ, okay? Equality of vectors. We talked about this in 2D. If two vectors are said to be equal, then that just means that each and every one of their components is a match, and you can set those individually equal to each other. Vector addition, similar to vector addition in 2D. You're going to get what we call the resultant vector, so fill in the blank here. The x component will be the sum of the x components of the two given vectors, operands, and then the y component, u2 plus v2, comma, and then u3 plus v3 is the z component. Great. You can also unitize a vector in 3D. Unitize is not a word, but it's the word I'm going to use when I'm asking you to take a vector and create a vector pointing in the same direction whose magnitude is 1. So similarly, you take your vector and you divide it by a scalar, which is its magnitude. So your final answer is going to look like a v1 all over the magnitude of v, comma v2 over the magnitude of v, comma v3 divided by the magnitude of v. And scalar multiplication is similar. Just as in 2D, if you're taking some scalar, pure number, multiplying it with a vector, you simply distribute the scalar. I think of it as distributing. That's probably not the right technical word for it. But here in 3D, here's a picture of the standard unit vectors for you. So the I hat, I sometimes call it I hat, pointing in the positive x direction. There's the x-axis right there. J hat is right here. And then K hat is pointing straight up in the positive z-axis direction. Okay, so any vector that you have here, v, can be written as a linear combination of these three standard unit vectors. Okay, so let's just do a quick example to reinforce these quick points. This is an easy example. You had this on a quiz, you should get 100% because it's like free points. Here are 2 points, an initial and a terminal point. Find the following: the component form of the vector AB. No problem. Component form, we use angular brackets. You're going to go terminal minus initial. So the terminal x coordinate, which is B's x coordinate, minus -2, that's A's x coordinate, comma, and now we take the difference of the y coordinates, terminal minus initial, and then we take the difference of the z coordinates, terminal minus initial. And your final answer is, after doing some arithmetic, there we go, 2 - 7, 3. Okay, letter B, same thing, but write it as a linear combination of the three standard unit vectors in space. So we already got the answer as far as, here's AB here. AB can also be written as 2I hat minus 7J hat plus 3K hat. And I'm done with letter B. Letter C, get the magnitude of AB, which is the length. So you're going to take the square root of the sum of the squares of the components. Now I'm purposely not putting a -7 squared. Why? Why am I kind of being fast and loose here? And I'm like, I don't feel like writing -7 squared. Anybody want to?
It's going to be positive even if you square it.
Good. Yeah. I'm lazy. I already know that -7 squared is the same as 7 squared. So forget it. I'm just going to do that. All right. So what is, square root of 4 plus 49 plus 9? Ooh, yucky. Yikes. Square root of 62. Okay. And remember, magnitude is always a scalar, pure number. Okay, letter D, find a unit vector. Unit vector, length is only 1, magnitude is 1, pointing in the same direction as V. Well, we already got the magnitude, so we kind of did half of letter D already. So the unit vector, we'll call it U, is going to be the X component of our vector divided by its magnitude, and then the Y component, -7 over square root of 62, and the Z component over square root of 62. And we're done with letter D, yay. And letter E, unit vector pointing in the opposite direction. So they basically are asking us for opposite of U or negative U. And that's just, we're just going to invert all the signs here.
Oh, sorry, Professor. For part D, was the 2 negative?
No, it wasn't, because this 2 up here wasn't negative. Remember 0 minus a minus
yes,
2?
yes.
0 minus -2. Okay. So, but then when we do negative U, since we're going to take the opposite in sign, we'll have that. Okay. Any questions so far on this problem, example 12?
We don't need to rationalize in 62.
Never. In my class, don't waste valuable time. I think I mentioned that in one of the lectures earlier this week.
Yeah. Now
you might be like, well, my teacher in algebra, she used to spank me if I didn't rationalize my denominator.
not. Yeah. I'm sorry.
I'm sorry you were traumatized in a
Yeah.
previous class. You don't have to. Now, if you do, because you just are thrown to do it, I'm okay with it. But then you're kind of waiting on a timed quiz or exam. You may be spending time for no reason. Now, and my math lab will accept both answers. That's one nice thing about my math lab. So if you do rationalize the denominators because you like to, fine, and you'll still get credit. Does that help?
Yeah. One more thing.
Yeah.
We don't have to. There's no perfect square for 62.
Well, go ahead and try factoring 62. I don't think he's got a perfect square factor. I'll let you figure that out.
Yeah. Okay. Yeah. I see it now.
That's about as good as he gets. Now, if he did, like let's say it was square root of 80, for example, that's one I just think off the top of my head that could be further simplified. You would want to further simplify it and reduce your fractions to lowest terms. But I think square root of 62 is not going to get us anywhere. Okay, now let's move on. Definition of parallel vectors. Super important to know if a vector is parallel to another vector or not. Super important and kind of basic. Now, visually speaking, it's obvious. So let me just draw you some pictures. Here's a picture of a vector V. Okay. And here's another picture of another vector W. It's clear that they're parallel, right? Like, yeah, they're parallel. They don't intersect. Fine. But here's another vector, say, pointing in the opposite direction of V and W. And I claim that all three of those vectors are parallel to each other. Yeah. So the point is the vectors can be parallel whether they're pointing in the same direction or exactly the opposite direction. Now, I'm not going to have you drawing vectors all over the wazooby and then going, okay, are these parallel or not? That's going to take too much time, and sometimes it won't be easy to tell if they're parallel or not. So what's a more analytical way of telling if two vectors are parallel? If they're scalar multiples of each other, people. And that's what this definition says. Two non-zero vectors, U and V, are parallel if there exists a scalar such that one of those vectors is equal to a scalar multiple of the other. So by the way, this inherently means it could be one or the other. Like, as long as you can prove to me that one of the vectors is a scalar multiple of the other. So for example, let's say U is equal to 10 times V. What would that mean? That means the same as the fact that V is equal to 1/10 of U. So either way, it doesn't matter as long as you can show me is a scalar multiple of the other. However, if they ask you for a specific scalar and give you a specific way they want it, then you can't just do either one of these. Okay, so what am I saying? Here's a vector W is given. Fine. Determine if these vectors are parallel to W or not. So this vector V, is he parallel to W? And if yes, give the C in such a way that V is equal to that C, that scalar times the W. So this is how I do it, people. I'm asking, is V equal to CW, where C is some scalar? So if I distribute the C over W's, oops, sorry, what am I doing? So if I do CW, what does CW look like? It looks like -6C, 8C, 2C. And the question is that equal to V? And where C is the same scalar each time. So we're going to use vector equality here. If this left-hand side vector is equal to the right-hand side vector because we have equality, what has to be true? Well, 3 equals -C, -4 has to equal 8C, and -1 has to equal 2C simultaneously. So we're going to solve for C 3 times in a row, and all 3 of those C's had better match. If even one of them is different, that means that those vectors aren't parallel. Okay, so solving for C the first time, we get 3 over -6, but that reduces to -1/2. The second time, we get C is equal to -4 over 8, but that also reduces to -1/2. So far, so good. And the last time we solve for C, we also get a -1/2. Woohoo! Success. So the answer for letter A is yes, V is parallel to W. That's a yes. Now, what about this other V in part B? Well, again, we want to check, does this V equal the scalar multiple of W, which we said was -6C, 8C, 2C. Are those two vectors equal where C comes up to be the same thing? So using vector equality, 12 is -6C, -16 has to be 8C, and 4 has to be equal to 2C simultaneously. So if we solve for C 3 times, and I'm reducing, oh, so far it looks like they're going to be parallel, huh? You think? What do you think?
Yes.
Careful.
No.
No.
No. Oops. We got a +2 there. Ah, bummer. Not parallel. Almost tricked you, huh? So the moral of the story, don't get too lazy and go, oh, if I, check out 2 out of the 3, 2 out of 3 is good enough for government work. No, you got to make sure all 3 are good. Okay, we're done there. And now let's do some other last minute things to wrap up section 13.2. So let's write this vector in component form. Now, this is a little bit tricky because it looks like they are giving us I and K, but where's the J?
It's
So
0.
True or false, would I be able to write this vector like this?
No,
No, that's incorrect. Why? That's false.
because that's supposed to be the J.
This is a 2-dimensional vector that I just wrote here, so definitely it's not. The fact that there was a k hat, the standard unit vector, that tells me that this vector is not a 2-dimensional vector, it's a 3-dimensional vector. So you're going to have to put a 0 in there to say that the J happens to be 0, okay? And this is now true. So this is the answer. Now, one of the things that I'll full disclosure here, I prefer component form. I prefer component form for the following reason. You are now ready for me to tell you why. When I look at component form, there's never any confusion about whether it's a 2D or a 3D vector, because it's clear how many components the vector has, and that corresponds to the dimension that the vector lives in. On the other hand, if you look at the standard unit vector linear combo, let's say I gave you a vector W is equal to just say 2i hat plus 3j hat. Looking at that description of the vector, it's not clear if that's a 2D or a 3D vector. It could be either or, unless somebody tells me. I'm not sure. It depends on the context, right? But just somebody giving me that vector, I'm not sure. And if it is a 3D vector, that would be very different from a 2D vector. So this is very confusing, because if it were a 2D vector, then it wouldn't have a third component. On the other hand, if it were a 3D vector, then the component form would be 2, 3, 0. Is this clear that why there could be a confusion with the linear combo format here? Now, I get that our physics brethren actually prefer the linear combo of standard unit vector format, and that's fine for those folks. I prefer component form because I never get confused when I look at my component form of what dimension I'm working in. So that's just a little side note that the book does not talk about that I'm going to tell you. These are the tips and hints that are important that I give to you in class. Now, let's do example 15. Example 15 is sort of a working backwards problem. And sometimes when I give this problem on a quiz, I notice that students go, I don't know how to do this. I don't have enough information. I'm confused. And I claim, no, you got enough information. It's just a problem we haven't done yet. So what I mean is they're giving you a vector V already done. And then they're telling you his initial point's coordinates. The goal, the unknown here, is what is the terminal point? The points are quantities that are just a dot, right? So let's say we'll call this Q, and since it's unknown, we'll give the coordinates of this point Q some unknown variables to work with. So what is X, Y, and Z in order for this to work? Well, you guys know that in order to create a vector, say P and Q, we're going to do terminal minus initial. So you take the terminal X coordinate, which in this case is unknown, it's X, and you subtract the initial point's X coordinate. And then you do the same with the Y's, and then you subtract the Z coordinates. And this, oops, that's an angular bracket, that has to be equal to V. But V's component form is 7, negative 1, 3. So if this vector on the left has to equal this vector on the right, we got equality there, we'll just equate the components. So this X minus a minus 2 is X plus 2, that better equal 7. Y minus 3 had better be the same as the Y component over there, negative 1. And the Z components have to match. Oops, I keep putting commas when I mean equal, sorry. And then you just solve for X, Y, and Z with these three little equations. Here we're going to subtract 2, we get X is 5. Here we'll add 3. So it looks like I'm going to get Y is negative 1 plus 3, which is 2. And here we'll add 5 to both sides, and we'll get Z is 8. So the answer is this terminal point Q has coordinates 5, 2, 8. And that's the answer to this problem. So it's kind of a working backwards problem. Okay, any questions so far? I'll look at the chat. Yeah, Sebastian, to answer your question, it depends on the context. And usually when you are working on my math lab or one of my exams or whatever, you'll probably be able to figure out what the context is, or they'll tell you. They'll go, well, consider the following vectors in space. And remember, space means 3D. Hopefully you get, right? Otherwise, we'll all be confused and it'll be horrible. Okay, example 16 is a little bit tricky, but I want you to be able to think about forces operating in 3D. We did a force diagram a couple of times last lecture. If you recall, remember we did the horsey problem where we had the horse pulling on a rope and then you pulling on a rope, and then we added those two vectors together in 2D. Well, what about doing that in 3D? It's kind of hard, but you can still do force diagrams, in physics, as a physics application in 3D. And this one's not too hard to do because luckily for us, they're giving us sort of, well, you'll see a nice third vector. So they're telling us that 3 forces act on an object. Okay, Two of the forces are at an angle of 100 degrees to each other and have magnitudes of 25 newtons and 12 newtons. Now, in the last lecture, the magnitudes that we were working with those forces were pounds, and that's true. That's the units for English system. And for those of you who've taken physics classes, you already know about this. But if you're working in the metric system, magnitudes of forces, if you're working in the mass newtons, in kilogram Newton system, second system, it's going to be newtons. Okay, that's the unit of force. Now, the third force is going to be perpendicular to the plane of these two forces, and that guy's magnitude is 4 newtons. Now, I'm going to try to draw this in 3D, and then I'm going to sort of look at the plane and kind of look at it and go back to 2D. So here's the plan. So here's 3D. You have 3 axes, X, Y, and Z. And the first 2 forces are at an angle of 100 degrees to each other. And it's like, well, where are they? They didn't give us component form, nothing. I'm lost. I can't do this problem. Yeah, we can. Let's take this XY plane here. This is the XY coordinate plane. And just draw it flat right here, because I can. Okay, let's just look at that portion. I'm gonna just be because I'm the person in command here. I'm just gonna say this first vector, say the 25 Newton guy. I'm gonna just say he just is pointing in the positive X direction, because I can. I'm just gonna go, hey, there you go. And this is a length of 25 because they told me 25 Newtons. So this point right here would have coordinates 25, 0. And so this force, I'll just call him F1, would obviously have components 25, 0, and he is working in 3D, so his Z component by default, since we're working in the XY plane, will be 0. Fine. Now, the other force, which is in the same plane, is making an angle of 100 degrees, so that's like kind of like right over here, okay? And he's only half as big because he only has a length of 12 newtons. So now it's not so easy to get the component form, but we'll call this vector F2. And from what I taught you last time, his component form can be found because it'll be his magnitude times cos of 100 degrees, comma, magnitude times sine 100 degrees. And because he's flat in the XY plane, it's understood that his Z component is zeroed out. And cos 100 and sine 100 are yucky numbers, so screw it, I'm just going to leave it like that. Now, the third vector is perpendicular to both of these guys. Whoa, geez, what does that mean? So now I'm going to try to draw these 2 vectors over here in 3D now, so that we'll come back to 3D. F1 is pointing in the positive x-axis, and remember, he's like a length of 25. And then over here, 100 degrees over here, is the F2 guy. It's kind of hard to draw in 3 dimensions on a 2-dimensional graph. And then perpendicular to both of those is a vector shooting straight up, and he's kind of tiny because he's only a length of 4 newtons, but he is perpendicular to both. I'll put little squares here. He is understood to be perpendicular to both of the original vectors because they're in the XY plane and the Z axis is perpendicular to the XY plane. And so we'll call him F3. And because the tip of his vector is located at the point 0, 0, 4, I hope it's obvious that his components are going to be 0, 0, 4, respectively. Yay! And so the question is, what would the magnitude of the force need to be to counterbalance all 3 of those forces? Well, let's see what F1, if we added F1 and F2 and F3 together, and we took its magnitude, essentially, I'm going to do kind of 2 things at once. We would do the square root of the sum of the squares of the components, and the components are going to be the sum of all 3 of these vectors. So if you look at the X component plus the X component plus the X component, all 3 guys is X components, add them together, we'll get 12 cos 100 degrees, yucky number, plus 25 plus 0, and then square that, plus, and then we add up everybody's y components, sine 100 degrees plus 0 plus 0. So that's just going to be 12 sine of 100 degrees. And then finally add up everybody's z components, okay, like that. And then square root this, you'll get something weird. And it's like approximately 26.092. And the units are newtons. And we're done with this problem. So you can kind of think in 3D there. This is just getting you a little bit acclimated to the idea of thinking in 3D. And having worked in 2D for so long, it might be a little bit trying at first, but you know, give it your best shot. Okay, now for a cartoon. So I love this cartoon I saw a few years back because you have to know vectors to even understand it. So Jason, and Super Bowl Sunday is coming up, so this is kind of good, football. Hey, what pattern did I tell you to run? You said to go 10 yards out and then 10 yards to the right. So if we were just drawing what the younger kid brother is a nerd, you know, go 10 yards out here and then go 10 yards to the, I'm going to the left, but let's just go to the left anyway. So 10 yards to the right or whatever. And so what pattern did you run? He says, I went 10 square root of 2 yards at a 45-degree angle instead. So what did the younger nerdy kid brother do? He actually did this. So he ended up at the same spot that the big brother wanted him to. So, and big brother says, and are they the same thing? And the kid brother says, yeah, if you add the vectors, sure. And then the bigger brother, this is football, not math class. And then he goes, why do you think I ran to 2 decimals? I'm sorry, I just thought that was funny. But, you know, you got to look for humor when you can. So I hope you can appreciate that little cartoon, okay? And if not, maybe you're just not awake yet and you need to have some tea or coffee so that you can get your sense of humor back. Because, you know, in times like these, folks, it's the humor that's going to get you through, right? Have you ever noticed that when you get mad or when you're upset, you tend to lose your sense of humor? Have you ever noticed that about yourself? Think about it. I notice when I get really upset, my husband, you'll meet him sometime. He's a joker. He always likes to tease and joke. He'll try to crack a joke and I'll tell him, wrong time to crack a joke. Not in the mood. That's because I lose my sense of humor when I get upset, okay? All right. We're moving on. Section 13.3. Who's with me? Are you guys still there?
Yes, we're here.
Yes.
Yes.
Yes, Professor.
You're still
Yeah.
around. Okay, let's take a poll. Let's take a poll, okay? Just for fun. Do you still have your teddy bear or doll? Okay, multiple choice. The choices are yes, but it's in the closet. Or yes, and he sleeps with me. And the other one is no, sadly lost. Never had one. And the last one is cannot remember. Okay, polling is going. Please vote. Okay. Are you guys voting? All right, everybody's voted. All right, cool. All right, the winner is, oh man, no, sadly lost. Guys, that's like something special from your past. Oh, well. Okay, I think I might have lost mine too, so.
When I was younger, all my sisters got lice, so I had to throw them away.
Oh, that's horrible. I guess that's a good reason to throw them away. Okay. All right, well, I guess a part of your past is no longer. Okay, bummer, man, bummer. Okay, so that was a fun poll. All right, so we're going to do the dot product, and we're going to look at what is the dot product. That's the easy part. And then the next thing is to look at some applications of it, like who the heck cares about dot product? It's kind of easy to do, but what's the use of it? And we'll do that today. Now, your quiz this weekend happens to only cover 13.1 and 13.2. So anything I'm doing starting right now with 13.3 won't be on this Sunday's quiz. Yay! However, it is going to be on the following week's quiz. All right. So, you do want to know it, so don't just fall asleep and go back to bed or anything. Okay, so now I claim it's going to start getting fun. This is where the good stuff starts. First, let's do some review. Okay, 2 review questions here. What we've learned so far. The result of vector addition is circle 1. Is when you add 2 vectors together, do you get a scalar or do you get a vector? Anybody remember?
Vector?
Vector is correct. You get a vector. Yeah, vector plus a vector, vector. Okay. How about when you multiply a scalar with a vector? Do you get a scalar or a vector?
A vector.
A vector, yeah. So both of them, you get a vector. Yeah, so what? What's the point? Well, watch. Definition of a dot product. Here we go. The dot product is also known as the inner product, although in this class, I'm probably never going to call it inner product, just truth be known. But I want you to be fully educated mathematical students. And for those of you who are going to take Math 254, or maybe you're in Math 254 right now, let's do a quick survey. In the chat, say yes if you are currently in Math 254, or maybe you already took it. Give me a yes. Okay, we got a no. Anybody else? Okay, Jay, yes, no, yes, no, yes, no. Okay. So those of you who said yes, who already finished it, you completed it and you're done. You're a graduate. Give me a yes. Okay, so those yeses, I assume, are in the class right now. Okay, so you guys are taking it right now. Fine. So here's the deal, linear algebra folks. You won't see inner product yet, but probably in about 2 months you will. And I'm going to say a couple things about that. There are many ways to define an inner product. Some legit, some not. In this class, it's always going to be defined what the linear algebra folks called as the Euclidean dot product. And that's the one we learn. But when you take a linear class, it starts getting really wacko because they'll talk about the Euclidean one that we do, and then they'll even introduce some weird ones. Good luck. Okay. So let's do the 2D version of dot product, and 2D and 3D are almost the same, okay? So if somebody gives you a vector u and a vector v with those components, when you take the dot product, you're going to see a little dot there. That's why they call it the dot product. And it's going to be the product of the x components, u1 times v1, added to the product of the y components. And this, folks, is a scalar. It's a pure number. The 3D version, you just jack it up for one extra term there. You're still going to multiply the x components together, u1, v1, add that to the product of the y components, and then add that to the product of the z components. And again, you're going to get a scalar, not a vector. The result of a dot product is what?
Scalar.
Scalar. If you were just listening, I just fell asleep again. I read some of about the syllabus quiz, and for those of you taking it, I ask you a few questions at the end, and one of them is, how are you going to stay focused among all the distractions of remote learning? Because there's plenty of it. I mean, I'm just one here, and you probably have 57,000 things at your house that you could get distracted by, or maybe that you'd rather be doing. I don't know. It's hard for me to compete with that, I'll tell you. I know, I've Zoomed. Zooming is terrible, but we don't really have any options. And pre-recorded lectures, yes, but those can be not helpful either. Okay, let's do properties of the dot product. Woo, yeah. So this theorem, some of it you may think, oh, well, it's obvious. Not necessarily. So check this out. If you were being asked to take u dot v right here, what is true? Well, the good news is it doesn't matter what order you take the dot product, you'll still get the same answer. That's cool. Now, folks, that isn't always true for other operations, because when we get to cross product next week, order is going to matter. So be careful. What if you're taking a dot product right there of the sum of two vectors? You could either do it like it says, like do the addition inside parentheses first, then take the dot product, or equivalently, you could distribute the u and take the dot product of u and v and add it to the dot product of u and w. Same. Left-hand side, same as the right-hand side. Fine. If you have a scalar c and you're multiplying it with a dot product, you could either do it like that, as is, or it's equivalent to first doing the scalar multiplication with the u and then taking the dot product with v, or you could take u and the dot product with the scalar multiplied with v. All three of those are equivalent. Whichever one is your personal favorite, go for it. And then 4, what happens if you take the dot product with the 0 vector? You're going to get a scalar, of course, but what do you think the scalar is?
0.
Yeah, true. And then this one, I put a double asterisk by for a reason, because you want to keep your eyeballs on this one, because not only is it weird, it's going to come up later in some other applications. It turns out that if you take the dot product of a vector with itself, you'll get exactly the same result as its magnitude squared. Okay, I'm going to prove 1 and 5. And so 1 is pretty easy to prove. If you take u dot v in that order, you're going to get u1 v1 plus u2 v2 plus u3 v3. On the other hand, OTH stands for on the other hand. If I take v dot u, I'll get v1 u1 plus v2 u2 plus v3 u3. So by the properties of real numbers, because real numbers are commutative, the I can't even talk this morning, commutativity property, u1 v1 is equal to v1 u1, et cetera, et cetera. These two are equivalent. And so therefore, we can indeed conclude that u dot product with v will always give us the same result as v dot product u. So we're taking advantage of the commutativity of real numbers in order to prove the commutativity, I think I forgot forget it. Commutativity of dot product. Okay, now what about the proof of 5? Like, well, are you sure that's true? Yeah, sure. First of all, if we assume that v is looking like v1, v2, v3, let's do the left-hand side and the right-hand side. What is v dot product with v? Well, it'll be v1 times v1 plus v2 times v2 plus v3 times v3. And using our knowledge of repeated multiplication, we can write that using exponents, okay? Save that for later. Now, consider the magnitude of a vector squared. So what is that going to be? Well, a magnitude involves a square root, and we're going to square that square root. And so remember, magnitude is the square root of the sum of the squares of the components. But you guys know from math, if you square a square root, you're just going to get the radicand. That's a fancy schmancy name for the stuff under the radical. Okay, fine. Now, what do you notice about these two expressions that I have? I want you to compare this guy with this guy. What do you notice? Are they the same?
Yes.
Yeah, they're the same. So therefore, 3 dots, we can conclude that a dot product of a vector with itself will always be equivalent to its magnitude squared. They're equivalent. Okay, fine. Now what? Well, now, how about you and a buddy? I'll put you in breakout rooms. You and buddy are going to get together and do the following problems, A, B, C, and D, where you're given the U and the V and the W here. Those are given vectors, and go have some fun and play with the dot product and some of the things that we talked about, okay? So I'm going to go put you in breakout rooms here. Let's see here. We'll go for 6 of these puppies. Doot, 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 doot. So remember the 2 things I ask of you when you're going to go breakout. First, please turn your microphones on so you could talk to your buddy. And if you don't have a mic, you need to buy one or call in by phone also so you can talk. and join the breakout room once I open them. Okay, so here we go. I'll see you guys soon. Bye. Hey, you guys get out of there. Those foods are not for you guys.
I think everyone's still working. Have you done the homework already?
For which one? The 13.1?
Yeah, well, both of them are open, but have you done them?
I finished 13.1 except on the last problem there was like solving the equation. I couldn't figure it out, so I was going to ask her for help on that one.
Okay.
And then I started 13.2, but some of the stuff we haven't covered, so I stopped I think on like 5 or 6.
Oh, okay.
Did you
Well,
do 13.1?
I did. I skipped the word. Oh no, I don't think I did. I'm not sure. I might have skipped the word problem. But yeah, I'm gonna go to her office hours. I've already pretty much completed more than half of the other one. But yeah, if you need help, let me know. Or she
Yeah.
can help you too, I guess.
Yeah. So you didn't do 20, the last problem then?
For 20? For
For
13.1?
13.1, yeah. Well, it wasn't the last, yeah, the last problem, number 26. I got to part C.
Oh yeah, I did do that.
Okay, so I got to part C where the last thing it says, now eliminate one of the scalar multiples. In this case, eliminate C sub 2. What is the resulting equation? I got the right answer, but now I don't know how to like isolate the C1 to get the, it says solve for the resulting equation for C1. I don't know how to do that. Like, do I factor out the C1 or something? Do I substitute? That's what I was confused about. Or I
Yeah,
was like,
I think you're gonna have to ask her then, because I wrote my notes, but I'm just like, what did I don't know. I need to figure out what I did.
okay.
Yeah, just go ahead and ask her that one.
Have we gone over how to find an angle, like given the components? I don't know. I'm mixing up my physics information with my calc.
Are you in the physics with who are you have taken physics with?
With Professor Lee.
Oh, I'm in the same class,
Oh,
I think.
oh yeah, probably.
Yeah.
But I know he has 6 classes.
Oh, never mind then. Wait, do you have it on Tuesday, Thursdays?
Yeah, at 10.
Oh yeah, we're in the same class.
Oh.
She did go over it. The way she does it is different. It's
Mm-hmm.
like on page 9, but that's where she explained like the theta for arctan. You have to add 180 degrees because of
Oh
the
yeah.
yeah.
Do you know how we do it though with 3 components? Because I was doing the homework on the physics, my math lab, whatever it's called. But I was doing it and it was 3 components, and then it was like find the angle between these 2 vectors. And it was
With the
3D.
physics one,
I don't think we've covered it, but I'm not sure. Maybe I missed it.
Yeah, I don't think we've covered it at the moment because he said he wanted to stay away from 3D at the moment.
Oh, okay.
I just know he was having us do like the trig stuff, but just
Mhm.
with 2 vectors.
Yeah, I understand the 2 vectors one, but then when I got like to the, it's still chapter 1 that I was doing, but it was asking about 3-dimensional, and then it was like find the angle, and I was like, oh my god, I don't know what to do.
Is it like that exercise? Oh, hi guys.
We're coming back here. Oh dear. That's weird. Okay. Okay, guys, are we back? Let me just check the breakout rooms. Did everybody get back? No, we still have a couple people that are still stuck in their breakout rooms. I think they haven't figured out how to leave yet. Okay. So I was going around to a few of the breakout rooms, and I was noticing that some people were on track and some people were a little bit confused about, and it might have been that the notation is rather new, so it's understandable if you're kind of stuck with some of this. So welcome back. So before we get to it, I was just talking to one of the students in the breakout room, and they said, oh man, I really got to review my derivatives and integrals from Calc 1 and 2. And I don't know if I told you guys this or not, but here in modules, if you go into week 1, you'll notice in week 1, I have what's called gateway review worksheets for derivatives and integrals. And I encourage you to look at this. And this will also help you get prepared for quiz 0, part A and B, which is just basically review of derivatives and integrals. So here I've posted for your pleasure a little worksheet for derivatives you can fill out. And then there's another worksheet for some fun integrals you can work on. And then here is the solution key for the derivatives. And then below that is the solution key for the integrals. And I think someone pointed out there was a slight error in my integration key. I think I forget where it is. Oh dear. I think this
Oh, I think it was on the integral one. Yeah, the integral.
This is supposed to be pi 24ths minus 1/12. I apologize. Forgot to distribute a negative here. So in your key, make sure that that is pi 24ths minus 1/12. Thanks, Hannah. And so that was that. So I just recommend you do that for yourself if you still need to brush up on those derivative and integration skills. Okay, back to reality here. All right, I think most of you got u dot v, and so all you did was you multiplied the x components and then you added that to the product of the y components, and then what the heck is 10 plus negative 16? Well, negative 6. So you got an answer of negative 6, yes?
Yes.
Yes.
Yep.
You got to be careful here. You already did u dot v in the previous part. So this is asking for negative 6, not dot here. I shouldn't even put a dot, just negative 6 w. There's no dot product, happening between the -6 and the W. This is called scalar multiplication. We already taught you scalar multiplication earlier in the week. We did? Yeah, we did. Remember? You're just taking the -6 and multiplying it with the vector W, -4, 3. So you distribute your -6 and you get a vector, not a scalar. The vector, answer to part B, is a vector 24, -18 with components, okay? Did anybody get that one right? Check the chat and tell me yes. Yes? No, no, no. Oopsie daisy, no. My bad. Okay, a lot of people did get it. Fantastic. Now, letter C is a little bit tricky because it also is going to have a dot product with scalar multiplication. But if I were you, I would do the scalar multiplication first. So you first want to figure out what is 2 times your V vector. So that's important that you kind of take care of that. So if you look at your V vector, 2 times the 5, 8 is going to give you a vector 10, 16. And then they want you to take the dot product of U with that. So you're going to go, oh, I need to take this vector 2, -2 and dot product that with the 10, 16 guy, right? And now you take a dot product. So you go, okay, 2 times 10 plus -2 times 16. And I get, what the heck is that? 20 plus -32. What the heck? -12? -12, final answer for letter.
Yes.
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 Okay, I'm glad to hear it. Now, letter D, I claim there were 2 ways to do it. You could have either taken the magnitude and then squared it, or if you were brave, I claim this is exactly the same as W dot product with himself, according to the property we just proved. So if you do this, you're just going to take the components and some of the squares of the components. So I get 16 plus 9, which is 25. Okay, and we're done with this problem. Questions?
Nada.
Okay, we're all good. Let's move on. So now that you're kind of clear on dot product and making sure you make the distinction that dot product isn't the same as scalar multiplication, and you might even have both of those operations in a single expression and be able to handle it when it hits you and how to do it, let's talk about applications. What is the dot product good for? A lot of things. That's why you're taking this class. I could go on, but you have to, up until the very last week of this class, we're going to be looking at dot product. Like it's never going away. Cool. So the first thing I want to go over is a real basic application, but powerful. It's going to be on the final, trust me. And it'll be on midterm 1, trust me. So one really awesome thing that you can use the dot product for is to figure out the angle that 2 vectors are making. So let me just draw a picture first. So if you had some vector U here, and these can be either in 2D or 3D, doesn't even matter. I don't care. Vectors in the plane or space. What the heck is this angle between them? I don't know. So it turns out that the angle between those guys is found by first finding the cosine of the angle between them. So the cosine of the angle between, that's a theta, is the dot product of U and V divided by the product of the magnitudes of U and V. So then, well, then how do you get theta? Well, you take cos inverse of both sides, and you're going to get the actual angle will be cos inverse of this lovely quotient, the dot product of U and V divided by the product of the magnitudes. Pretty good, huh? I don't have time to prove it, but you do need the law of cosines, because what you do is you basically take this triangle with the other leg being U minus V, and you perform the law of cosines on it, okay? It's going to take me some time to do that proof. If you are a math major, you probably do want to see it. Come to office hours. I'll be happy to do it for you. It's not that hard. It's kind of fun. Now, let's do the alternative format of this theorem. If you rearrange this theorem where you kill off the denominators by multiplying both sides by this denominator, you get u dot v, that's a dot, is equal to cos theta multiplied with the product of the magnitudes. Well, who cares? It's just, you're not doing a new thing. This is the same, but it depends on what the context is of which version you'll use. If somebody wants to find the angle between two vectors, I use this version. Okay. If somebody gives me, wants the dot product of two vectors and they're not giving me the component form of either of the vectors, but they're giving me an angle and a couple of magnitudes, I can find the dot product of those two vectors without even knowing their component form, which is kind of cool because it'll be this answer here, this product. Now, before we do some examples, let's talk about this version of the theorem. Hopefully you saw in the previous example that it's possible for dot product to be equal to a negative number. In fact, dot product can either be positive, negative, or zero. It's not limited by anything. So when is it going to be positive, negative, or zero? Where if you look at this formula and you use your knowledge, you use your knowledge of cosine, and also you use your knowledge of what magnitudes are, you can tell what the sign is going to be of your dot product, or if it's going to be zero. So in other words, since magnitudes are always positive, the magnitude of u times the magnitude of v is always going to be some funky positive number. Okay. Well, cosine can either be a positive, a negative, or zero. You know that from trigonometry, right? So when is cosine positive, negative, or zero? Because basically, whether this entire product is going to be an overall positive, negative, or zero is going to rely on what cosine is doing. He's sort of going to be the one driving the bus there. Because if he's positive, this entire product will be positive. If he's negative, then a negative times a couple of positives will be what?
Negative.
Negative. And if cosine is zero, which cosine sometimes is a zero, zero times anything is?
Zero.
Yay! So let's look at some pictures. I want you to see the geometric representation of all the different flavors of this angle. So here's, there's going to be 5 cases all the way across here, so leave room. Case number 1 here. Let's say you had u pointing that way, and so there's u, and let's say v, I'll use a different color so they don't blend. Let's say v is pointing in the exact opposite direction. I hope it's obvious to you that the angle here is 180 degrees because these two vectors are pointing in opposite directions, so which is also the same as pi radians. But what is cosine of 180 degrees? I believe it's -1. So that would mean that u dot v would equal to some negative number. What negative number? Well, that depends on the lengths. Okay, so that's case 1. That could happen if the two vectors are pointing in opposite directions. What's case 2? Case 2 would be where the angle between the two vectors is what we call obtuse. You guys have probably heard of an obtuse angle. So that means it's more than 90 degrees, okay? Obtuse angle. That means that the angle theta here is greater than pi halves, but less than pi. So what is cosine for angles that are obtuse? Does anybody remember from their trig? Cosine of an obtuse angle, is it positive, negative, or zero? Anybody know? I'll check the chat.
Negative.
It's negative. It will be negative because when you're in quadrant 2, your cosines are negative. I hope you remember that. You know, like cos of 3 pi fourths is negative, right? So that would mean your u dot v would be some negative number. Okay, negative. Okay, case number 3. What if your u and v are exactly 90 degrees? There. What is cos of 90 degrees or cos of pi half? Same.
0.
0. So what would the dot product be between two vectors whose angle between them is 90 degrees?
Also be 0?
0.
Yes. And this is super key. I put a box around that. In fact, when this happens, the vectors are orthogonal to each other. And you got to learn this new vocabulary word, orthogonal, because you're going to hear it starting today till the day of the final. Orthogonal. It kind of means the same as perpendicular, although perpendicular is a word we can only use in 2 and 3 dimensions. You couldn't even use the word perpendicular in 5 dimensions because we can't picture 5 dimensions. But the word orthogonal is good for any dimension. And it means 90-degree angle, baby. Okay? Now, the fourth case is when we have an acute angle, not cute, but acute. So say U is pointing there, and let's say V is still pointing there. So let's say this angle theta is an acute angle. And that just simply means that it's greater than 0, but less than pi halves. So what is cosine of an acute angle? Positive, negative, or 0 from your trig class? You know, like cos of pi fourths, for example. Is that positive, negative, or 0?
It's gonna be positive, right?
Yeah. So what does that mean that this dot product will be? Overall, it'll be some positive number. And finally, the last case, case 5, what if U and V are both pointing in the same exact direction? Like this. So they're kind of like that. So the angle is 0. What's cos of 0 equal to?
1.
1. So that would mean the dot product of two vectors who are pointing in the same direction is going to be some positive number. That's all. So we're done with all the possibilities. And now let's do the definition of orthogonal. I kind of already gave it to you, but let's do the official definition. Vectors U and V are orthogonal if U dot V is equal to what?
0.
0, right there. In other words, cos theta is equal to 0 because theta is 90 degrees, pi halves radians. This is key right here. Key forever. Super key. Okay, I'm going to finish today's lecture with example 2, and then we'll get out of here, okay? You have a fabulous weekend after we complete example 2. I will post this recording in your Canvas to this afternoon for sure by tonight in case you want to review it. Just a quick poll. Has anybody gotten a chance to review any of the recordings that I've posted yet? I know it's been a busy week, so maybe not. Has anybody checked it out?
I actually had to because I missed some
Nathaniel, you have? Not yet, not yet. Okay, Aaron has. Were you able to access it okay without having to enter a passcode, Aaron? Was it okay? Yeah, okay. That's good to know. I'm just checking because another class had an issue and I had to like, oh crap, and I had to go into settings. I don't know how it got set to having a passcode. You should not need a passcode to watch my videos, okay? Just go in there and watch them. Have I told you about my YouTube channel yet?
YouTube channel.
No.
I didn't talk about that. Okay. Sorry. Last semester, I basically posted all of my Zoomed lectures. Not only did I post the links, but I took extra time to download them and upload them to YouTube. And now I can't even access them because YouTube changed my account behind my back, which was not very nice of them. And I can't access those videos anymore. But if you go to YouTube, like so, and you type in, okay, first you go to YouTube. What the heck am I doing? YouTube's really changed a lot. So I may be posting I'm kind of mad at YouTube because it seems like they deplatformed me. What the heck? So like if I go to my videos, they don't show up anymore because they took away my my Hotmail account. I can't see, or maybe I can. Let me just see something here. Now I can. Oh, I'm zooming with an IT guy later today. This pisses me off. So if you see these chicken, you know I like chickens, right, guys? Remember I like chickens?
Yes.
Of course. And why? How the cluck do I do this? If you go to Professor Rasky and you just search that, let's see if it comes up. It doesn't want to do it. So what should come up if you type in Professor Rasky here, and let me get out of studio. I don't know if I can get out of there. Let's just go to dashboard. So if I go to Professor Rasky, if you do this, it should come up with the playlist, and it looks like nothing's coming up here. I don't know why.
I see it on my YouTube. I see your account.
You can see, hopefully you can see my account, and those are last semester's videos, and I can't vouch for, you know, the because I changed the course reader a little bit in a different location, so it won't be exact, but it might be something that you may want to go to. Okay, so that's another alternative way to look at the lectures. But the ones that I'm doing for you, I'll post the links for. Okay, all right, so back to lecture. Let's finish it out. They're giving us 4 vectors, u, v, w, and r. Oh my God. Find the angles between the following pairs of vectors and then answer the following: orthogonal, parallel, or neither. Okay, so u and v, if you you know the cosine theta is going to be u dot v, that's a dot product, divided by the product of the magnitudes. So I'm going to do this on the fly. So we're going to go 3 times -4 plus -1 times 0 plus 2 times 2 all over the product of 2 square roots, square root of 3 squared plus 1 squared plus 2 squared. And then this one's the square root of 4 squared plus 0 squared plus 2 squared. And this is a hot mess. This is what? -4 over square root of 14 times square root of 20. And that's not the answer. Remember, that's cosine of the angle. So the angle is going to be cos inverse of this weird number, and you can take the product of those to get the product of 70, square root of 70. And make sure you're in degree mode, because you won't be able to figure out. This is 118.6 degrees. Okay. Now, does that mean the 2 vectors are orthogonal, parallel, or neither? And parallel will mean they're either pointing in the same direction, the angle would be 0, or it would mean they're pointing the opposite direction, 180. Since they're not orthogonal, this ain't 90, and it's not 0 or 180, so that these 2 vectors are none of these possibilities. How about u and w? So cos theta is going to be the dot product of u and w divided by the product of the magnitudes of u and w. Fine. So it turns out that when, so I'll just leave these magnitudes here for the moment. I want you to notice that when you take the dot product of u and w, you get 3 plus 1 plus -4 all over the product of their magnitudes. But what does that numerator end up being? That's why I'm not wasting valuable time figuring out the denominator. Look at what the numerator is going to be, people. You notice the numerator is 0? What does that mean? Well, this is equal to 0. Well, then what? Well, cos theta equals to 0 means theta is cos inverse of 0, which is
Orthogonal.
90 degrees, and these guys are orthogonal. Woohoo! And I give you the answers down here. Now, V and R, when you do their dot product, you're going to go the dot product of V and R, -4 times 2 plus 0 plus, that's 0. That's a big fat 0. Plus 2 times -1 all over the product of their magnitudes. Okay, fine. And what you're going to get is you're going to get the numerator is -10. When you do the product of their magnitudes, you're going to get a square root of 100, but that's -10 over 10, which is -1. And then theta, oh, sorry, I'm trying to go too quickly. Theta is cos inverse of -1, which is 180 degrees. And that tells me that they are in fact parallel. Okay, the last thing I want to leave you with is of something that's not in your course reader. This is not in your notes, but I want to give this to you anyway because I may put it on a quiz, and I don't want you to go, oh, I don't know how to do that problem because you didn't give it to us in class. And okay, so here's a little example. Suppose you're given some vector named u, and they're only giving you his magnitude, and some other vector, say named v, his magnitude is 3. Okay. And let's say the angle between them, they're giving you that, is pi/4. Find u dot v. Huh? Well, if you use that alternate version of the theorem that I taught you, that u dot v is the same as cos theta times the product of the magnitudes, and they gave you all your information here, you're going to go cos pi fourths 2 times 3, but I think cos of pi fourths is square root of 2 over 2, and then 2 times 3 is 6, and then you'll reduce this to lowest terms. Final answer, it looks like the dot product is 3 square root of 2. Can a dot product be a yucky, weird number like 3 square root of 2? Sure, absolutely. Why not? As long as it's a real number, it's fine. In this class, anyway, we're not going to do any complex numbers in this class. Okay, I'm done. So if you want